Good morning and welcome to the EasyPower Thursday technical webinar. Today our guest speaker is Claudio Mardegan with Engepower Brazil. The material today is the second of a two-part presentation. If you missed the first, the link to both recorded webinars will be sent to all who registered for this session today. There are two subtle characteristics of Claudio's presentation that I find very appealing. Rather than trying to sell anything, he's sharing knowledge and wisdom gained from years of experience. And second, he does not hold back on lessons he has learned the hard way. Feel free to submit questions and Claudio will respond via email. During the last session, Claudio explained how to determine the time interval for proper coordination of relays, breakers, and fuses in a system using zone selective interlocking. We pick up the discussion today with section 11 as he explains additional factors to be considered in system coordination. Thank you for attending today's session.
Where to apply the coordination time interval? Coordination time interval, the general rule, the rule of the thumb, you apply the coordination time interval at the voltage short circuit current that the protective device is being sensed. This is very important, that is being sensed. Because if it's not, the current is being sensed, he's not seeing that value. The decision between what current we are going to use, half a cycle, 5 cycles, or 30 cycles shall be used depends on the protective device trip at the short circuit current. So, coordination time interval we apply at short circuit currents, but for the bolted fault. This is the rule of the thumb. But sometimes we have, this doesn't mean that we don't have to consider the other currents. We are going to consider other currents. One of the topics we are going to talk about here is about the arcing current. And the arcing current, it's very, very, very special because normally it's about half of the voltage value or lower. So if we have half of the value, the time to trip takes longer. If it takes longer, the destruction is higher. And also the risk of personal injuries. So we have to apply special techniques for arcing currents that we are going to talk here. This is a very interesting example for those who are starting in protection coordination. Here you have the protective device 1, protective device 2, and protective device 3. If we fault the bus at this point A, the relay that should trip first would be the number 1. If this relay fails, it should be the 2. If this fails, should be the 3. My question here is, relay 3 shall coordinate with what relay? 1 or 2, but you receive a coordination study that the curve 2 is below the curve 1. So this coordination study is not so good, but is not at your jurisdiction. You are the owner of this relay, so this relay shall coordinate with 1 or 2. If you look just at the TCC, you are going to say that you have to coordinate with relay 1 because it's the highest curve. For this reason, I put this example here. You have to start knowing how to analyze. If we fault the point A, what the relay that should trip? The 1. Who really does? The 2. So this relay will not trip. If I fault the point B, what relay should trip? Relay 2. So it's relay 2. The meaning of that is that relay 1 here doesn't matter what the setting of relay 1 is. The important here, when I have series elements, I have to coordinate with the immediately downstream. That's what we have to hold, what we have to understand. Series elements independently of the setting of the below, the downstreams devices. I have to coordinate with the immediately downstream. That's what I talk here in this next slide. Coordination between incoming and many outgoing protective devices. This is a typical radio system. When I have one incoming and many outgoing feeders, I have to coordinate with all of them. In other words, I have to coordinate with the envelope of all of them. Software doesn't perform the envelope. So we have to plot all of them and coordinate with all of them. 2 incoming feeders and 1 outgoing feeder. This situation, you may see that's not so common, but I will tell you that is more common than you think. Why? Because here may represent a bus is a tiebreaker. If tiebreaker is closed, you have 2 incoming, and for each outgoing feeder, you have 1 outgoing feeder. So it's more common than you imagine. And the big issue here is the current that each device will be sensed. Here, you see, if you have a short circuit here, the device 1 will be sensed by the sum of the currents of the incoming feeders. So the current here will be higher than the current in incoming. In this situation, how we do the coordination? Well, to explain this, I prepared the next slide. 2 incoming feeders plus outgoing feeder. In order to simplify the calculations, I put the pickup of the relays at same value of 100 amps. So relay 1 is 100 amps, 2 the same and 3 the same. The short circuit current for that the device 1 is being sensed is 2,000 amps. 2,000 amps. That is the sum of 1,200 plus 800. Relay 1 was given that its trip time is 250 milliseconds. And I have to coordinate these devices. I used here the IC very inverse curve equation. That is this equation here. This is the time dial. M is the multiples of pickup value. And if I want to determine the time dial, I have to multiply the time I have to coordinate times this and divide by this. So this is the equation. For relay 1, the short circuit current that is passing by its in its CT is 2,000 amps. Its pickup is 100. So the multiples of the pickup setting is 20. So my time dial will be the time of relay 1 that was given 250 milliseconds, multiplied by 20 minus 1, divided by 13.5. So the time dial will be 0.35. Relay 2, I do the same. The short circuit current is 1200, divided by 100 is 12. To coordinate two digital relays, I add the coordination time interval of 250 milliseconds plus 250 milliseconds, 500 milliseconds. Multiply by 12 minus 1, divided by 13.5. 0.41 is the time dial. And I do the same for relay 3, and the current is 800 divided by 100 is 8, the multiplier. The incoming have the same time, is 500 milliseconds, multiplied by 8 minus 1, divided by 13.5, we get 0.26 for the time dial. I am showing you now the TCC plot for this coordination. This is here the curve of relay 1. This relay 2 is this one here, that's over the R1. And the relay 3 is under R1. The question is, I will ask you if they are selective coordinated. If you just look at the TCC plot, you are going to say that they aren't coordinated. But I can tell you that they are coordinated because they are seeing different currents. Let's analyze. When the device 1 is being sensed by a 2000 amps current, it trips in 0.25 seconds. At the same time, the relay 3 is being sensed by 800 amps, and it trips in half a second. So 0.25 seconds and half a second, this relay will trip after this one. So it's coordinated. In other words, what you see here is not what you get in practical field, right? Because practically the relay 3 will trip after relay 1. And relay 2 also. So sometimes if we put all the relays to see the total current, you could see them completely coordinated. For this reason, when you have tie breakers, you have to provide a second setting group. Because if you open the breaker, the incoming will see the same current as the outgoing. The coordination point will change. So the time dial will change. Importance of correct is the actual value of short circuit current. Here, it's very important. Imagine you calculate a short circuit current here, in this current here in the middle. You provide the coordination time interval to guarantee the coordination between the device 1 and the upstream. If the actual value is lower than the calculated value, so you set your relay with this coordination time interval. One day a short circuit happened and the value of the actual short circuit is lower than you have calculated. your device is going to trip is lower. And the meaning of that is that you are going to have more destruction, more incident energy, and more time to repair, and more loss of production. So it's not good. If the short circuit calculated is lower than actual value, so the actual value is higher than the value you provided in your study, the device normally are inverse time. For higher values, you miscoordinate here because the coordination time interval maybe it will not be enough to guarantee the coordination. So you can have miscoordination here. That's why when you perform a short circuit study, if it's done for specifying any device, the most important are the highest value. But if you are performing a short circuit study for coordination, it's not the highest, but the most near of the actual value that are important. Arcing fault core importance for protection and coordination. Everybody knows that the arcing current is much, much lower than the Overcurrent fault. So most of the studies I see in my life, the people that perform the study doesn't plot the arc current on the TCC, and it's very important. Next slides we're going to show why. Arcing fault current importance for protection and coordination when we are setting low voltage time delay and definite time overcurrent below the arcing fault. For bolted fault, the device trips here. What we do here, for arcing fault, it would trip very, very high. So if the short time delay pickup, I set it below the arcing fault, independently if the fault is a bolted one or if it's an arcing fault, it will clear the fault at the same time. So this technique will guarantee that the incident energy will be as low as the bolted fault, as low as for the arcing fault. The same for using a second element with definite time. So what we do here? Normally, if you receive a short circuit study and a coordination study, you may have low voltage circuit breaker curve here, and the relay curve here, and the upstream relay here. Using the optimization technique, you set a second element with definite time. So you are both relays will trip at the same time for bolted fault and for arcing fault. This is very, very nice because our incident energy and all our closest categories will be lower. Here we have also a very interesting situation. You may receive a coordination study. This is the highest outgoing feeder relay curve and was applied for the bolted fault coordination time interval. This guy here used this technique, the optimization technique for arcing currents. The question is, are these relays coordinated? Looking at these curves, one may say they are. They are. But I can tell you that they aren't, because here I have one inverse time element plus one another definite time element. They are independent. They count the time independent. So the softwares for coordination normally cut this curve here. But in actual world, this element will continue counting the time. So the coordination time interval is not enough anymore, because with this trip time, both may trip and you may have a miscoordination. EasyPower prepared for this. It shows this part of curve here. The part above the definite time element, it cuts because this one will trip first. But from this point and over, it plots this curve. So this avoids some miscoordinations. That's why EasyPower software for this issue, it's very, very nice. I like very nice this feature. Another important thing that people takes a little time to understand, sometimes when you energize a transformer, the inrush current trips the ground fault elements. And why they trip sometimes? Most of time is application error. People sometimes put residual connections of CTs in low resistance ground systems, and you may have this kind of situation. But the big issue here is the current that relay is being sensed. So the big problem is that inrush current have a lot of harmonic orders, mainly second and fifth harmonic orders. So it's very important when we set our relays that we check this checkbox here, provide harmonic restraint. So this is one manufacturer. Here's another one, are the places where you can do this when you are setting your relays, providing harmonic restraint. Another issue is coordination issues regarding relay reset time. If you use electromechanical induction disk relay upstream, and downstream you have a digital relay. If you have an intermittent fault here, both pick up, both relays pick it up. So they start counting the time. But since the fault is intermittent, the fault is removed, the digital relay, if not correctly configured or set, will be reset instantaneously. But our induction disk relay will reset linearly because of its spring. So he starts moving back to the standstill position. But when the disk is in the middle of the travel, the fault starts again. The upstream relay is in the middle of the travel. So to trip, it will take much less time than from the standstill condition. And it trips first than the digital relay. So this is a situation where you have this kind of problem. So the upstream relay trips first. What you have to do is to set the reset time for the digital relay to emulate the behavior of the induction disk relay. Another interesting thing, neutral resistance ground system. with ground sensor scheme and long cable length. This happened in a plant. Before showing this slide, I prefer show the issue, and after we move back. Here is a plant where there is a very long cable here, and single line ground fault happens here. The relay settings are in this TCC. Because here is delta, this relay is instantaneous. This one also the same thing. And the relay that's in the neutral, I provide a delay for it here in order to coordinate with the instantaneous of the outgoing feeders. Normally here I have a 400 amps resistor. Here there is another knowledge also. Neutral resistor. Normally, if you don't declare to the manufacturer what's the permanent continuous current that this resistor shall be able to carry, the manufacturer will say that it's 0. So if any current stays more time, you can burn this resistor. And if you burn this resistor, the big issue is that you open the neutral. If you open the neutral, your system becomes unground. If the system becomes ungrounded, your ground elements will not be sensed by the ground faults. And you may also have transient overvoltage. So when you specify a resistor, ask to the manufacturer to provide at least 5% of continuous current relative to the short time current of the resistor. So 5% here is 20 amps. So this relay was set to 20 amps. We should never put over this value because you can burn this resistor. I am very upset because most of these studies I read, people set this relay here as much as 75 amps, 100 amps. The guy doesn't know this specific issue. So 20 amps. What happened here? What happened here was the following. A ground fault happened here. When a ground fault happened here, due to the resistor, the voltage in the unfaulted phases will grow up about square root of 3. So when the voltage grows up, it's going to appear here a charging current 3IC0 due to the capacitance of the cable. And the capacitive current for this cable here, XC, will be the value supplied by the cable manufacturer, divided by 5 kilometers. I have 906 ohms. IC0 will be the line to ground voltage divided by XC, 8.79. 3IC0 will be 3 times that value. It is 26.38. The outgoing feeders are set for 15 amps. So this feeder will trip as well. So for a short circuit here, this this circuit will trip also. And this is not correct, and this is not desirable. So when you have low resistance ground system and long length runs, it's very important you know if you have to take care of the situation may happen in your system. And the critical length cable may, if you have length lower than the calculate here, probably you won't have problem. But if your conductor's length are greater than the value you calculated here, you are going to have problems. So this is the critical length for you to be a base for you in order to take care of this situation I explained right now. What are the solutions? Add an intermediate delay for the elements on the feeders with long lines, but this is also increase the neutral relay delay. You may use directional ground fault relays, because here the fault will be in the opposite direction, not towards the load, but towards the source. So you may use directional elements. Or set the figures of the ground fault relays with a setting that is within the maximum total charging current. But you have the 20 amps that are your limit. So in this case, you could not do this. The same thing happens in snubber installation. Nowadays, a lot of transformers are burning due to switching of vacuum breakers and small length of cable. So these overvoltages are burning transformers. And to solve the problem, people are performing snubber studies and snubber installation. And if your system is low resistance ground or high resistance ground system, the same issue of capacitive current here, because the snubber is installed as near as possible as the transformer. So you may have problem here and trip during ground fault in other feeders. So you will use the same technique we provide in this slide here. Another issue that impact in the coordination is the plants where you have zero crossing, and this happens near generation plants. What happened? Big generators normally have big X over R ratio. This means high DC offset during short circuits. The problem is that the DC offset is so high that the alternating current does not cross the zero. It will cross the zero very, very far from the beginning, after sometimes 150 milliseconds. If I send a trip signal to the circuit breaker to trip in a time before it crosses zero, it will open the contact but will not trip, and you may explode the breaker. So this is a big issue. There are some solutions. One of them is you buy a breaker that can withstand this trip here, even not crossing zero. But this is a big circuit breaker. Here is about 3 meters, and here 3 to 4 meters. So it's a big equipment, and the cost is also huge, right? Another solution is to delay the time, but if you delay the trip, you can check if stability issues will be a problem or not. But when performing this analysis, the X over I ratio is the determinant in the DC offset. So you must correct this value of resistance with temperature, because you have a more actual value compared with calculated value. And another thing that nobody does is in the R of X over I ratio, they don't add the arc resistance. If the arc resistance is included, it will decrease the X over I ratio and will result in a reduction of the delay. There is no standard that specifies how to consider or represent the arc resistance. That's why nobody put this. In this kind of analysis, the electrical power system is represented at no load because it leads to more conservative protection time delay. These delays are normally in the range of 100 to 250 milliseconds. Another very interesting thing is the integration of this study of short circuit coordination, arc flash studies, and short circuit. Here, if we perform a short circuit study and also a coordination study, if I open my TCC here, we have this protective device curve is relative to this breaker. This one here is the R1. R1 is this one here. And the blue curve is the R2 relay. I can ask to the software to calculate the short circuit here. I click here. It shows the short circuit for half a cycle, 5 or 30 cycles. The problem here is that if I ask for the incident energy here, I will have 40.1 calories. So there is no category of clothes that protect any worker. In my language, value is dangerous, right? Here, so 40.1 is too much energy. One can say, put an arc relay here and you solve the problem. Okay, it's a solution. But you received this study, it's coordinated. Huh? You received this study, it's coordinated. You have the time intervals. If you want to know if they are coordinated, I can put here the values. They are coordinated for bolted fault. But for the arcing fault, it trips very, very delayed. What I'm going to do here, set a second unit with definite time. So if I click here, double click here, and ask to calculate the energy, and I click here, I set another element here with a definite time. Now you see my arcing fault will clear the fault at the same time as my bolted fault. The incident energy decreased, and now my closed category, now I have a closed category to protect the worker. Just changing a setting without any other procedure. It's very important that the guys that are performing the short circuit studies and coordination studies do these studies integrated with arc flash studies, because you are going to have more adequate settings and incident energies and much better production and things like that. Okay? So, conclusion and recommendation. The application of the explained techniques improve a lot the coordination study and incident energy study. The result of item 1 is that item 1 is this one here. As a result of item 1, the faults may be cleared faster and consequently equipment system personal protection is enhanced. Another important conclusion is that if the fault is faster removed, the destruction is lower and mean time to repair is thus improving the plant production. Correct application of protective device promotes more flexibility to protection engineer who will perform these studies. Coordination trainings are fundamental to analysis engineer, but they are also important to application and design engineers. Guys, thank you very much for attending this webinar, and I thank you everybody for the opportunity of sharing these things with you. Bye-bye. See you later.